good to see that the numbers haven't dwindled so much. So Ilya will continue with his series of lectures, and he's going to tell us about colored Jones polynomials. Could we get some white chalk? They have on the small.
This will be fine.
Yeah. I think we're okay for this round.
Then so Tejas is here.
So I'm going to introduce the screen here to the presentation.
So let me start with just a quick review of what we were talking about last time. So we looked at the Jones polynomial. The notation, we have this notation, k of t. And this is our polynomial, right? It sits in, so I guess I can say this, sits in t plus or minus 1. So you can have square root t's if you have links of an even number of components, judging by the Skein relation. In this case, here, like I said, L. In this case, the input L is an oriented, unframed. So this is the original Jones polynomial and the original variables. Then we talked about the Kauffman bracket. Polynomial. This is normalized minus a to the minus 3. Bracket d. This sits in Laurent polynomials in A. Okay. And here d is unoriented. So this is now the next gadget that we're going to see is going to be the colored Jones polynomial. So in the notation, so we're going to see the colored Jones polynomial late in this talk and in the next talk and then in several other talks. But if we want to see the Jones polynomial as a colored Jones polynomial, so the Jones polynomial is one of the colored Jones polynomials, then the notation is usually changed a little bit, and the notation is the following. So the Skein relation here is different. So the Skein relation is going to be of the form Q, I'm going to use the notation J2 of L plus minus Q inverse J2 of L minus is equal to Q to the 1/2 minus Q to the minus 1/2 J2 of L0. So this is a typical kind of notation here. And in this case, we get J2 of L sits inside as a Laurent polynomial in the Q's. I'm sorry?
When you say unoriented link, then
Yes.
how do you say right? The positive crossings and negative crossings, don't you need the orientation to say that?
No. For the Kauffman bracket?
No, the WD.
It is because you wrote that the WD, you wrote minus a minus 3W. So for that you need the.
Oh, yes, you're right. So this is unoriented in the case of a knot. You don't. It doesn't matter. For a link, you do need an orientation. Yes. So, yeah, you're right about that. So yeah, I guess it's for if it's a link, yes. I guess you do need an orientation for the ride. My apologies. For a knot, you don't. Okay? For a knot, you don't. For a link, you do. Okay. The change of variables here is that A is q to the 1/4, and it is t to the minus 1/4. Okay? And here, L is, again, oriented unframed. Same L as for the Jones polynomial. OK, so how do you relate this notation, this sort of colored Jones polynomial to this Jones polynomial? The change is the following. So I need to just, this is like a little dictionary here. So J2 of L in Q is minus 1 to the number of components minus 1 VL of Q inverse. Okay, and this is mu is the number of components. Okay, so here this is the little dictionary of how to get from the color Jones from the usual Jones in that variable to the color Jones polynomial, and then moreover we normalize. So in this case, what we get is J2 of the unknot is q to the 1/2 plus q to the minus 1/2. We don't want that, so what we do instead is we normalize and we define, let's call it Jn prime of L to be Jn of L over Jn of O. And that way, for the unknot, this guy is 1. So we kind of normalize. We divide by the value of the unknot. So this is going to be the notation for the color Jones polynomial. OK, there's some more notation. Let me introduce that later. Should I do that now? Let me do that now. Just a little bit more notation. So n with braces is going to be q to the n over 2 minus q to the minus n over 2. N in brackets is going to be n in braces over 1 in braces, which is q to the n over 2 minus q to the minus n over 2 all over q to the 1/2 minus q to the minus 1/2. Okay? And we have factorials using this notation. So this factorial is equal to 1 times 2 times n. And n factorial is 1, 2, up to n. Okay? And so what we have here is we see that J, so for example, we would write something like Jn of the unknot, the colored nth Jones polynomial of the unknot, would be written like this.
So we haven't yet defined Jn. So here like Jn.
That's correct. I'm giving some notation before giving. Yeah, so I'm going to give a definition today, and then I'm going to give a different definition next time. 2 different definitions, which are the same. OK. So this is all notation. Let me give you a little bit of background. And this was mentioned in a talk yesterday. So where this came from is Witten, in 1989, suggested a generalization of the Jones polynomial to links in 3 manifolds. And so this is, the idea was, it was a kind, so this is Witten, 1989. Suggested a kind of, I'm going to wave my hands and say, he kind of suggested turning quantum field theory into topological quantum field theory. And in so doing, he suggested taking the Jones polynomial and turning it into an invariant of a 3 manifold with a link inside that 3 manifold. All right, so that was kind of his idea. This idea was realized in different ways. So there was work by Turayev and Viro And this uses spines of 3 manifolds. And you can think of spines as giving you the same kinds of information as a polyhedral decomposition. So it's let's say triangulation. So Abhijit talked about triangulations of 3 manifolds. That's the kind of input you would need to compute the Turayev-Vero invariant. A different idea was by Reshetikhin and Turayev. Okay, and this used the whole quantum group machine. Okay. Just for fun, I just want to point out to you that there are a lot of Fields medals on the board at the moment. So Jones, Witten, quantum groups came from Drinfeld, and then the Thurston machine also. Thurston got, so we're talking now, what are we up to, 5? 4. So all of this work happened around the same time in the early 1980s, and I don't think any of these people knew that their work was at all involved. It's kind of interesting that it all kind of happened at around the same time, and then it came together much later. It came together, the idea, this volume conjecture, you saw when that was. That was, what, about 18 years ago, something like that? So anyway, it's kind of a fun way to see mathematics converge. So this was one method, 2 realizations, and then there's a third realization, which was by a French group of mathematicians, Blanchet, Haberger, Maasbaum, and Vogel. Let me just say that. And then at the same and separately Licorice. Okay, and this is using Skein theory. Okay, so what I would like to do in today's talk is explain this point of view for using Licorice's approach, and then in the next lecture explain the Reshetikhin-Turayev kind of quantum group point of view, although I won't talk about the Reshetikhin-Turayev invariant. I'll only talk about the color-Jones polynomial from the quantum group point of view. Let me just say also that the color-Jones polynomial is for S3. So this is a rather general theory about 3 manifolds, but we're only going to focus on S3. Okay? All right. The best exposition for this talk today is probably in Licorice's book. So Licorice has a very famous introduction to knot theory, and that is the best place to learn about his point of view, because that's what he presents. He presents his approach. Okay. So So last time we talked about the Skein algebra, R2n, which is the temporally-Lieb algebra, TLN. And let me just remind you what the generators and relations there are. So we have in this algebra, we have a bunch of generators. Well, this one is 1, and then this is E1 up to En minus 1. So these are the generators in the algebra, and they satisfy relations. So EI squared is delta EI. EI plus 1 EI is equal to EI. And EJ is EJ EI if they're far enough apart. Okay. So this is what we were doing last time. What I would like to do today is show you a very particular element in this algebra called the Jones-Wenzel idempotent, and show how that can be used to do more stuff. Okay? So to motivate this, so Licorice gives an existence proof of the Jones-Wenzel idempotent. He gives a theorem that says such an object exists. What I would like to do is to not start with that existence proof because it doesn't give you any intuition for what the heck it is. I would like to instead switch back to the representation theory of the Jones polynomial and show you where it comes from in the representation theory, and then show you the existence proof. Kind of it's not necessary to do both, but I'd like to show you the two perspectives. So this requires a bit of algebra. So just a little bit of algebra. So let's start with this. So TLN is a semi-simple algebra. Okay. And therefore, one of the properties of a semi-simple algebra is that irreducible representations, so IREPs, irreducible representations, are in one-to-one correspondence with what are called minimal central idempotents. Okay, let me unpack that expression. So this is just sort of pure representation theory of algebras. So,
So these are representations into what?
yeah, so this is again, representations into matrix groups, right? So this is.
Complex? What's the
Yes. So, yeah. So what I want to say is, yeah. So this is. Yeah. So this is over any complex vector space. So this is just any complex vector space. So for example, here. So just to put some notation. So these are idempotents which using Jones's notation. I'm going to switch notations a little bit later. But in Jones's notation, these are pi sitting in TLN. And how many are there? There are exactly, I is between 0 and over 2, like that. Okay? So what is this? What do these three words mean? Okay? So if I have an idempotent, this is a projector. This is what so pi, this is an element in the algebra such that pi squared equals pi. Okay? Central means that pi x is x pi, right? So for all x in this algebra. And minimal means that if pi can be written as a sum of pj plus pk, then that implies that pj equals 0 or pk equals 0. Okay? So these three properties come from, so this is an existence statement. So there exist such gadgets for every irreducible representation. Okay. Moreover, for this particular setup, in this particular algebra, these are orthogonal idempotents. Okay? They are orthogonal in the sense that pi pj equals 0. Okay? And they have another property, is that the sum of all of them is equal to 1. So this is a requirement. This is a very general algebraic statement. And this is particular to these von Neumann algebras, these particular TLNs. So this comes from the representation theory. This comes from special properties of these algebras. So people sometimes call them orthogonal idempotents. People sometimes call them minimal central idempotents. But we're talking about the same object. What do they look like? So here's what they look like, just to give you a sense of like what are we talking about at all. in TL2, okay, P0 is equal to 1 minus 1 over delta E1. And then P1 is just 1 minus P0. In TL3, P0 looks like this. 1 minus delta over delta squared minus 1 times E1 plus E2 plus 1 over delta squared minus 1 E1 E2 plus E2 E1. And again, P1 is 1 minus P0. Okay? These are not going to come intuitively, like sort of like obviously. So they're complicated. These are complicated gadgets. And the first one of these, P0, is the Jones-Wenzel idempotent. Okay, and now we're going to switch notations because we're going to go use Licorice's book. And in Licorice's notation, we will use, so this is typically given by Fn. Okay? We will also use the notation, which is now very common in the literature, of put a little square around n and put a little box like that. So we're going to use, I'm going to show you how you use P0 uses and how these guys are used. Okay? So hold off on this notation. I just want to point out to you that we're going to switch notations. Okay? Let me show you one application. Okay? Let me show you an application of the Jones-Wenzel idempotent.
So you mean in different TLNs, you got each P0 to be a
Yes.
Jones-Wenzel idempotent?
Yes. Yes. That's correct. Is that, did everybody understand the question? P0 is an element in TLN. Okay? All right. Let me show you how these are used. I'll show you how Jones used them. This is even better. I'll show you how Jones used them in his original paper. Okay. Okay. So there's a very important element in the braid group called the full twist. Okay. The full twist, sort of pictorially, here's the twisting operation. Of course, this is not a braid, right? But you do the belt trick. You pull it tight, right? If you do this to a belt, lay your belt flat out and then pull it tight. What happens is that you get this. All right. Right, you get this twist. Okay, so that's the full twist on the braid group. And if you write it in algebraic notation, using the Artin generators, it's usually denoted like this. This is, without the square, this is a half twist. So you take a half twist, and then if you square the half twist, you'll get a full twist. But in the Artin generators, there are many, many ways to write this. The full twist can be written in many, many ways in the generators. Here's a very standard way to write this. Sigma 1 to sigma n minus 1 to the nth power. Very standard way to write this. And what this is writing it like this. You get the idea? So this is n times. So this is this notation. Okay. So this is the full twist. The interesting thing about the full twist in the braid group is that it generates the center. Okay? This is the center. It's a central element, and it generates the center of the braid group. And as such, right, the image of delta of this full twist, right, in any irreducible representation is a scalar. Okay, again, this is a representation theoretic sort of statement. If you have a central element, then its image has to be a scalar. And so, if you take a representation rho of delta squared under the irreducible representation, then it follows. This is a kind of it's a generalization, I think, of Shor's lemma. But of what happens is that this becomes t to the ki for some coefficients ki times these minimal central idempotents pi. So in any irreducible representation, you can decompose this into the minimal central idempotents with some coefficients, okay, with some scalar coefficient. In fact, the ki is easy to figure out. Jones computes this in his paper on the Jones polynomial, and it's simply I times n minus I plus 1. It's not very complicated. I don't care, but I'm pointing it out to you. This is not that hard, okay? Now here's a consequence, right? So this is really interesting, that the full twist can be decomposed into scalars times these orthogonal idempotents. So what do you get then? If I take m full twists, do m full twists, then we're going to play with idempotents. This becomes the sum over t to the ki pi to the mth power. And then we expand this using the way that my students in my algebra classes expand. They just forget about all the cross terms. And so what you get is this is t to the ki times m pi. Okay? What just happened here? At this point right here, I'm using the fact that different pi times pj is going to be 0, right? And pi to the m is going to be pi. So what you have then, right, is what this is saying is that this is equal to, right? So this is, here's the amazing statement, right? So now this is already fairly interesting, but now here's the implication. I'm sorry?
All the PIs are elements in C of PI.
Yes, that's correct. Yes.
So when you say it generates it, it means that every PI is some power of the sector?
No, because these are elements in the algebra, and this is an element in the braid group, and this is a representation. Okay? Okay. Now, let's take this bilinear pairing that we saw earlier, right? D1, D2 is D1 union D2. Right? So we're taking a bilinear pairing where I take some element in here, right? I do something, I don't care what, and I take some element in here, right? And I do something else, whatever, and then I pair them up. Right? I take this bilinear pairing, right? In this bilinear pairing, here's what we can do. I can take any braid beta and take the full twist in the braid group and pair it. So take any braid and add a full twist. Okay? Right? So this is of the form right? So when I pair this using this machinery, this algebraic machinery now, what do I get is I get a sum of t to the ki m, right, exactly this guy, times a pairing with beta with each of the pi's. Right?
No, you apply rho to that.
I applied rho to this, but this is what this is. Remember, this is the representation. This is the TLN representation.
Yeah.
Okay?
So then beta.
So this is the representation, right? This uses this representation rho from Bn into TLN by taking beta to bracket beta. Okay? Closure. Okay? Okay, so the important point here is this is independent of m. However many twists I put in, this piece of it is independent of the number of twists. So all you need to do is compute this once. You compute this once, and you can figure out twist operators. And so what Jones did is he used this. This is a theorem. This is, again, in this, when he discovered the Jones polynomial, this is what he did. He used this procedure to find the Jones polynomial of torus knots, PQ. So immediately he found the formula for all torus knots using this exact procedure. And the formula is, I'll just put it on the board. It's, you know, just to show you what the formula is for torus knots. Okay.
Rho beta instead of beta. Here in the his PIs are in the algebra, PLN.
Yeah. So I guess what I should do is I need
Beta
to.
is a braid.
Yeah. So yes, it is a braid, and I'm taking the Kauffman bracket with elements with these various PIs, things like this. So I'm going to take a braid, and then I'm going to have some PI. And I'm treating this as, this is a linear combination of elements. But we're going to suspend our concerns about that and just treat this as a single gadget, and then take the closure. Okay. And then take the Kauffman bracket of that.
So is it just like beta bar union pi bar?
Yeah, you can do that. Yes. Yeah, that's what this pairing is. This is like the basic pairing. Okay. So just for completeness, here is this. We're not going to use this, but just so you know, p minus 1 q minus 1 all over 2 times 1 minus t squared times, and what goes in here is 1 minus t to the p plus 1 minus t to the q plus 1 minus t to the p plus q. Okay? And that's the formula, that's the closed formula for any torus knot of the Jones polynomial, the standard Jones polynomial. And this is the procedure that he used by breaking it up into these minimal central idempotents, these orthogonal idempotents, and using their property to compute this twist. You will see this as a theme. The only families of knots and links for which infinite families are known, the Jones polynomials are known, involve some kind of twisting. Twist knots, whatever, various families of knots, like pretzel knots, things like this. Everything that involves twisting. And fundamentally, it is this fact. The full twist is central in the braid group. And therefore, when you have twisting, right, you can compute these kinds of invariants using this type of Shor's lemma argument. And you will see that if you kind of spend some time in this field, twisting is an operation that's computable. You can compute things. And there's a very interesting analog in the geometry. Twisting is a geometric limit, it turns out. So Abhijit hopefully will tell us about this. There's a Dane-Surgery theorem. Volume converges under twisting. And that is a very interesting sort of thing that comes together here. All right. So this is a motivation for the Jones-Wenzel idempotent. What I would like to do now is to turn to the axiomatic approach where licorice shows you that these exist. Now, we've seen this coming from the representation theory, but let me show you now from the Skein theory point of view. And then we're going to use them to construct the color-Jones polynomial.
So the representation of Bn and Tn, that is the irreducible representation.
Yes, so this is it's a little confusing. This is a representation into TLN, and then I'm using these objects in TLN.
So that representation is irreducible.
Yes, well, I'm taking this representation that we're doing. Yes, Bn into TLN. Yeah.
Is it obvious that this expression, the first sum, is a scalar?
These are the scalars. So these are scalars.
Yeah, but you want it to be a scalar operator in terms of operator, according to Schur's lemma.
I'm sorry, I don't understand the question.
So image of this central generator of the center
Yes.
should be a scalar.
Yeah, it's a scalar times each minimal central idempotent. All right, let me go on. Maybe we can talk after. Okay. So, all right. So now let AN sit inside TLN. And this is the algebra generated by E1 up to En minus 1. We've omitted 1. So everybody except 1. All right? All right. So we're going to construct. We want this element Fn. I'm switching notations, right? In TLN. All right. So this is, you can think of this as, right, this little box gadget like this sitting inside the Skein algebra of R2n. That's kind of the best way to think about this. Okay, so this is a linear combination of objects that we're going to treat as one. Okay, and so the proposition in Licorice's book, this is lemma 13.2. Okay, so this is lemma 13.2 in Licorice's book, is that if a to the 4k is not 1, so again, we have to always avoid certain roots of unity because the representation theory is just different there, then there exists a unique Jones-Wenzel idempotent sitting in TLN such that we have the following properties. Okay? Fn on this algebra AN, right? AN Fn is 0. This is a weird statement. If you don't have 1 in your expression, if you just have some product of the generators EI, then the Jones-Wenzel idempotent will kill them. All right, so it looks like this. The graphical picture looks like this. If I have n, and I short circuit it anywhere, then I get a 0. Any short circuit gives me a 0. Okay? Property, so this is the statement that Fn EI is 0 for all I. Okay? Property 2 is that 1 minus Fn sits in the algebra generated just by the e's. The third property is the idempotent property. Fn is Fn. And graphically, this one looks like this. So graphically, if I draw a little box and then draw a little box over here, then that's the same as just drawing one little box. Okay, that's the idempotent property. More generally, let me just make a comment here. This is part of a more general picture that if I have a little box, if I have the I plus j idempotent, and I have a little I idempotent and j strands, okay, then this is equal to just the I plus j idempotent. Okay, so this is a special case of this. Okay? All right. And the fourth property is that the closure of this idempotent, which sits inside of C. So what is that statement? That fourth statement is the statement that if I take a little box and close it, then this is an element of S of R0, which is C. Okay? All right, so these are the properties that Licorice proves. Okay? So we have some examples on the board here, which are, essentially from him. Yeah.
Isn't even to a minus 1 the generator of even?
Yes. Yes. These are, except one. One is also a generator.
Okay, so you only removed easy.
Only removed one. Yeah, only removed one. Okay. So you can look at his book for the proof of this. I'm not going to prove it on the board right now. But it's the proof of this is an existence argument, so I'm going to let that be. But what he does is he then shows us an inductive formula, which is the key formula for dealing with this fellow, this Jones-Wenzel idempotent.
What is Fn bar?
The closure. This is this guy. This closure.
And why is it a number?
Okay. So here we're going to for this inductive definition, I need one more notation. Fn1 will be this guy. There's the nth idempotent plus one more strand. So this sits in TLn plus 1. And so the statement, the inductive formula is that Fn plus 1 is equal to Fn1 minus, I got to give this a name. Let's give this a name. I'm going to use Licorice's notation. This is going to be, this element is going to be delta n. I apologize for that. This is not the braid operator. This is not a braid. This is a number. It's a complex number. It's change notation. I'm going to stick to Licorice's book, though. Because if you go read his book, this is all over the place. And he does not mean the Garside element, the half twist. So if you read a book on braid theory, capital delta N is always the half twist. If you read a book in whatever, quantum topology or something, that's not what it is. It's something else. It's very it's terrible. But anyway, this is that guy. So this is this minus delta n minus 1 over delta n Fn1 En Fn1. Okay? This is hard to parse. There it is on the board. There's a full statement. That's hard to parse. Graphically, it makes much more sense. Let me show it to you graphically. The n plus first Jones-Wenzel idempotent is equal to the nth Jones-Wenzel idempotent with one more strand minus delta n minus 1 over delta n times this gadget. What is that graphically? Graphically, it looks like this. n, where n minus 1 strands come down to the next idempotent. Then this goes up, and this goes down. Okay. So this is just one little strand. Okay, so that's that picture. Okay, so that's the inductive formula for the n plus first idempotent from the nth idempotent. Okay, it's complicated. Sorry. Okay. All right. Let's now use this. Okay, so now let's use this. Let's take the Skein algebra of S1 cross I. So this is going to be S of S1 cross I. And if I draw this, it may be helpful to draw it in another color. Okay. Here is my S1 cross I, some annulus. And let's take an element in here, in this annulus. Okay. We'll call this element alpha. So it's just the generator of pi 1 of S1 cross I. Okay, that's our element alpha. And you can see that what's going to happen in this Skein algebra is this is just a polynomial algebra in alpha. That should make sense, right? All of the crossings you can dispose of using the Kauffman bracket relations, but you can't do anything with this single crossingless loop. Okay? Okay. We want a map from TLN into this Skein algebra by taking the Jones-Wenzel idempotent and mapping it to that guy. Okay? That's going to be the map of interest. This fellow here is Sn of alpha. Right? It's some polynomial in alpha. Right? This is an element in. Let's figure out what polynomial it is. What's the polynomial? Okay, and this is what licorice does. So the trivial cases are S0 of alpha is just alpha to the 0th power, which is just 1. S1 of alpha, well, the Jones-Wenzel idempotent on one strand is the one strand. So S1 of alpha is just alpha. And what's going on generally? In general, we need to use this nasty relation. Right? So let's use this. I want to show you how to use this nasty relation. And so in general, what you're going to get is you're going to get something that looks like this. I'm going to make this short. Again, the details are in Licorice's book. Okay. Okay. This guy minus delta n minus 1 over delta n of this guy. All right, something like that. And now, over here is where you can do some manipulation. Here is where you can use properties of the idempotent, isotopy, moving stuff around. And what you get is you get the following, that this is equal to this guy minus this guy. Let's write it, right? So it's equal to this fellow minus that fellow. This is a step that requires some computation. So I'm skipping a computational piece. There's some identities. You're using the idempotent property. And so you get that guy. So what that tells you is that Sn of alpha, this fellow, is equal to alpha times Sn alpha, which is that guy, minus Sn minus 1 alpha. So that's the identity. Thank you. Thank you, thank you, thank you. OK? Does that make sense? I'm sorry? Because there's one more strand. There's one more alpha. So you get this identity. Sn plus 1 of alpha equals alpha Sn alpha minus Sn minus 1 alpha. And of course, everybody looks at this and says, ah, it's a Chebyshev polynomial. I'm kidding. You're supposed to do that. This is the recursion relation for the second Chebyshev polynomial, for the type 2 Chebyshev polynomial with a change of variables, obviously. Okay? So this is a Chebyshev polynomial. And the recursion relation is the following, right? So what you see is in polynomials, S0 is 1, S1 is x, S2 is x squared minus 1, and S3 is x cubed minus x squared minus x plus 1, and so on. And you can keep doing this recursively. So these are a certain family of Chebyshev type polynomials. Okay, they are exactly a Chebyshev polynomial with some variable change. As a consequence, we can figure out exactly this fellow. Do you see? The whole point is to figure out this value. We can now figure out that value. And here is the value. Right? It turns out that delta n is equal to minus 1 to the n, a to the 2n plus 1, minus a to the minus 2 n plus 1, all over a squared minus a to the minus second. Okay? That's the formula. Okay? And what's more is it turns out that these Sn alphas are a basis for the Skein algebra of the annulus. Okay? Yes, I'm sure you're right about that. Okay, like that? Okay, thank you. Okay, so in this basis, with exactly this value, everything is now explicit, right? And so what we're going to do now is we're going to construct the colored Kauffman bracket polynomial. Okay, so this is the construction for the colored Kauffman bracket. We're going to define a bilinear form from the Skein algebra of the annulus into here.
How do we get this delta n?
Because we know exactly now this Chebyshev polynomial.
Sn
Yeah. Yes. And so we can construct this Kauffman bracket by doing the following gadget. Okay. Given a let me do it as a kind of a picture. Okay. So if I take a framed link, okay. All right, let me take some framed link. I'm going to put some numbers on here that indicate some additional framing. Right? So here's a link, and here's a framing. You can think of it as a push-off. Right? This is I want to push off a longitude from this component with linking number 0. I want to push off a longitude from this one with linking number 1. I want to push off a longitude on this one with linking number 3. You can really think of them exactly as push-offs with a given linking number. So I'm given a link L, and I'm also given some numbers, k1 to k mu, where mu is the number of components of the link. Okay? And so what happens is that this map that I want, is exactly the map put in the idempotent with each number and take its closure. So what am I doing? I'm taking this link and I'm inserting a little idempotent, Jones-Wenzel idempotent. So if that's a 3, I'm going to put in a 3 here. If that's a 1, I'm going to put in a 1 here. And if that's a 0, I'm going to put in a 0 here. Okay? And now let's interpret this. So so I just performed an operation. So this is the operation, and then I'm going to take the bracket of that fellow. Now, let's do an interpretation. What does 0 mean? 0 means nobody's home. There's nobody there. So I erase that component. 0 means that component's gone. Okay. What does 1 mean? 1 means it's just that component itself. And 3 means put in the Jones-Wenzel guy here. So what I'm doing is I'm computing the bracket of this fellow. And that's an element in here. That's the colored Kauffman bracket. Okay? Because 0 by that rule. By that rule. Okay? Okay. So now, how am I doing? I'm doing terrible on time, aren't I? Can I go over just a few more minutes? Okay. All right.
What is the meaning of saying given this k1, k2, k mu, that whatever was given like 0, 1, 3,
Yes.
why is it given?
It is the input. It is the input for this invariant. You have to give me a framed link with the numbers are the framing.
So for each component, the color is different?
Yes. In this case, yes. Okay. In general, that won't be the case. We won't be doing that, but it could be.
Okay.
I think this is fine. Yeah. Okay. So let's return to this full twist operator. So what does that look like, right? So the full twist looks like this then. Let me do it sideways. So this is the full twist on n strands. Then what we saw at the very beginning is that this is equal to some scalar Cn times this guy. And so Licorice computes that scalar from his point of view. Okay? So it turns out that the scalar is equal to, it's not very complicated, minus a to the n squared plus 2n. So this is not surprising to us anymore, because we know sort of intuitively that this is a minimal central idempotent, and it's going to be a kind of eigenvector for the full twist operator. And so this is the eigenvalue, so to speak. Okay? All right. And so what this lets us do is this lets us generalize the Kauffman bracket approach. Remember what we did with the Kauffman bracket. The twist means that we need a framing adjustment to get a link invariant. Let's do exactly the same thing. It's this theme keeps repeating, that the twist gives us a framing adjustment, and we can get a link invariant using that. So what we need to do is, right, so do you understand what I'm saying? So we saw, let me just, a quick review. So we saw that this guy was minus a to the third times this guy, right? And we adjusted by the rive. So let's do the same thing here, right? If we adjust this now, here's what we're going to do. We will define the color-Jones polynomial. This is the Skein theoretic definition of the color-Jones polynomial. Jn plus 1 of d is equal to Cn, so this twist guy, right, to the power minus the rive of d, right, that's the framing adjustment, times the colored Kauffman bracket over there. Fn, Fn. And here we really do take the same color on every component. Right, so the nth color, we take color n, we take the nth Jones-Wenzel idempotent on every component. And we compute this. And this is the definition of the color-Jones polynomial. So then we normalize. So I guess this depends on the diagram D. Right, I give you some diagram that depends on the diagram D. And then we normalize so that Jn prime of L is equal to Jn of L over Jn of the unknot. Okay. So computationally, right, so what we need to do is we need to understand how to compute this guy. And this is the key identity. So using the notation, this is the notation from the very beginning of this talk. This is with the quantum factorials. Okay, this is equal to this fellow here. Okay, so that's the right. Thank you. Yes, absolutely right. Okay. No, this should be right. Unless I'm off. Please check. Okay, but I believe this is correct. Satoshi, is this right? Thank you. Oh, plus? Okay. This is plus? Okay, thank you. I love this audience. Great. All right. Anyway, this is the recursion formula. And then what we want to be doing, there are lots of other formulas. Let me give you just a very quick sense of so we have trivalent formulas. So a trivalent diagram labeled with ABC is a diagram that looks like this. So this is ABC, okay, and this is IJK. So this is so you can get a little trivalent diagram like this. And there are all kinds of formulas that involve these trivalent diagrams. So I have a whole sheet of little formulas, but let me give you an example. Let me show you one example of such a formula. What does such a formula look like? So using this notation, what you can show is that if you do A, B, C, D, and some j here, this is equal to the sum over these 6j symbols, A, B, I, C, D, J, of this guy. B, C, A, D, I. Stuff like that. So you have these kinds of little fusion, they're called fusion formulas. And this is in this book by Kauffman and Linz, where there's a bunch of them that are explained, defined, and so on. But this is, in practice, how to compute color Jones polynomials from this point of view. You basically have a bunch of little diagrammatic things and symbols here that fundamentally are coming from these quantum factorials. The asymptotics of the quantum factorials is what makes the volume conjecture difficult. It's that it's very difficult to get closed formulas for these invariants. And so in these very special cases, almost all of them involving some kind of twisting, you can do it. Okay? So let me stop here. So this is one point of view of the color Jones polynomial. This point of view does not explain anything about this n. And so in the next lecture, I'll show you that that comes from the dimension of a certain representation. Okay? But this is computationally a more sort of, has been a more fruitful approach for actually computing stuff. Okay? All right, thank you.
Maybe next topic 10:20.
Any questions?